welcome everyone. We're happy that you're here for the first session of the Argonne Leadership Computing Facility Intro to AI-Driven Science on Supercomputers. My name is Paige Kinsley. I work at the ALCF at Argonne, and I will sort of be the facilitator of each session. Today, what we're going to do, I'm going to do a quick introduction to Argonne, to the series and series expectations, and then we'll hand things off to Huihuo Zheng, who is our first presenter. So with that, let me share my screen and we can get started. So like I said, hi, my name is Paige Kinsley, and I'm going to do sort of a very brief introduction to Argonne National Laboratory and sort of what it is in the grand scheme of science, and also the Argonne Leadership Computing Facility, which houses all of our wonderful supercomputers. So there are 17 different Department of Energy national labs across the United States, and each national lab has a number of functions, but the main focus is delivering world-class research, technologies, and new knowledge that aim to make an impact from the atomic to the human to the global scale, and sometimes to the cosmological. Argonne National Labs is where all of your session instructors are from, as am I, and Argonne is located just outside of Chicago, Illinois. And Argonne's focus scientifically is very broad. We do science from the subatomic all the way up to the cosmological, like I mentioned, and everything in between, all sort of focused around energy generally. So something that some of you may know in some capacity, thanks to a movie that came out last July called Oppenheimer, Argonne was actually the first national lab from the Department of Energy and was born out of work on the Manhattan Project, which was developing essentially sustained nuclear fusion nuclear fission. And Argonne came out of work done at the University of Chicago, specifically the Chicago Pile, which was essentially the first sustained nuclear reaction that was ever produced. Specifically, it was actually done under the football field at the University of Chicago. Fortunately, we've since sort of moved things a little bit further out of the city. So what is the Argonne Leadership Computing Facility? We are housed inside Argonne National Lab, and we are a national user facility that brings in researchers from across the globe to do science on our world-class machines. What it allows people to do is pursue scientific challenges at a scale that they wouldn't necessarily be able to otherwise. We also have many in-house experts from many different domains that can sort of help users who come in do the best science that they can. And all of our resources, all of the machines that we have at Argonne as part of the ALCF are dedicated to open science. And what that means is that folks who apply for time on our machines and get allocations can do all of their science fully for free as long as they publish the work that they're doing, which is pretty unbelievable as far as access of these machines. So just to give an overview of the history of the Argonne Leadership Computing Facility, and sort of the evolution of the technology that we've housed here. Back in 2004, we had our first machine, an IBM Blue Gene L machine, that had a computational power of 5.7 teraflops, so about 10 to the 12 flops. For scale, most like Apple Mac laptops at this point, running at sort of max capacity, run about at 1 teraflop. So obviously, in the past 20 years, we've moved pretty significantly forward in terms of technological advancement in our computers. The current machines and the current machine that you all are going to have access to and are going to be working on is Polaris. Polaris is a 44 petaflop machine. So we've now increased things by about 4 orders of magnitude since the very beginning of what we had at the ALCF. And Polaris is a machine that all of the nodes are heterogeneous, so they have both CPUs and GPUs. And sort of our next big machine after Polaris is Aurora, that some of you may have heard of. Aurora is currently #2 in the world's ranking of the fastest supercomputers, the most powerful supercomputers in the world, with a theoretical capacity of running about 2 exaflops. So again, moving 3 orders of magnitude faster than sort of what the standard machines that we have here are now. However, we're going to be focusing mostly on doing all of the work that we have on Polaris. You'll also hear some during this series about our AI testbed and sort of the next generation technology that we're doing specifically to advanced AI and ML work. Maybe. There we go. So something that you'll hear a lot about and that sort of the series is centered around is this idea of AI for science. And you'll see actually a lot of different examples of sort of what's being done here at Argonne in applying artificial intelligence to scientific applications. But I wanted to highlight just a couple that have been done at Argonne recently. So things that you can do for in applying artificial intelligence for science is potentially predicting virtual drug responses in cancer cells, mapping neuron networks from electron microscopy data, and then also understanding the complex crystal structures with neural networks. So all of these things can be done with AI, and when we scale them up to the using supercomputers, we're able to do significantly broader, more impactful data. So this series, you'll hear from a number of different experts sort of within specific domains who are applying AI to their science. So one question that you may have is, what are we actually going to touch on this series? Hopefully most of you have sort of gone through and seen at a high level sort of what's going to be touched on, but I wanted to sort of introduce you to the faces, if anything, of the instructors that you'll be hearing from. So all of the folks that you see here are Argonne staff working at the within computing at Argonne and are experts within AI and ML in some capacity. And they'll be going over sort of the fundamentals of AI, especially the fundamentals of the math behind AI and ML, what the fundamentals of neural networks as well, sort of expanding that out. We're going to also focus later on in the series, learning about large language models, how to build them and sort of what their applications are. Generally, why we need supercomputers in AI training instead of just running on your local machine, and sort of how to run large scale things on supercomputers when it comes to AI as well. So the general structure of each week is sort of going to look like this. We'll start at 3 p.m. Central each Tuesday. And then from 3 to about 4:10, we're going to be introducing essentially the session content and the hands-on content that will be led by a specific Argonne instructor each week. And then in the final 20 minutes of each session, we're going to bring in an Argonne scientist to sort of talk about specific science that they're doing in applying AI on supercomputers. Each talk will generally be about 10 minutes with the opportunity for all of you to ask questions afterwards, which is great. So some of you may be wondering, okay, how are we actually going to run this? What's the format, the expectations, and sort of the logistics of things? You've probably heard at least some of this before, but I'm going to repeat it anyway to make sure that everybody has heard it at least once. So for logistics, one thing I would ask you to do now, if you haven't yet, is please change your Zoom name that's currently listed right now to your first and last name. The first and last name that you registered with. This is going to allow us to sort of track who's being able to attend each session, which is really helpful for us. And also will just give us a good idea of who keeps on coming back for more. Something that was asked in the chat, and then I'm going to reiterate here, is that questions should be asked in the Slack, not on Zoom. And the reason for this is that Slack will essentially be able to keep the history of questions as they're asked. Zoom obviously will go away at the end of every session. This will also allow people to ask maybe more involved questions, even around specific things around code and access to Git and all of that sort of thing. So Slack is the best thing. Each session has a specific Slack channel that you can sort of ask questions specific to that as well. Hands-on activities. each week are generally going to be run on our Jupyter Hub on Polaris, unless stated otherwise. Huihuo, I think, shared in the Slack that we have the opportunity for those who might not have access to the machines yet to use Jupyter Colab to run the hands-on things this week, and generally it's going to be run on Jupyter Hub. For materials, so the guides for each week, the session materials, and hands-on exercises are all going to be posted on the series GitHub, which is posted on the series webpage and also has been sent out through a couple of emails. Some of these guides include how to submit homework, which I think a lot of you have sort of already worked through, how to access ALCF systems generally. So if you're still trying to work on that, try to figure that out. There's a lot of detailed information on how to do that. And then also using Jupyter Notebooks for those who are not familiar with it. Something that was also asked in the chat, yes, each session is obviously going to be recorded. That's what's happening right now. And the recordings and slides and any materials are going to be posted by the end of each week after each session. So if you're not able to come live, you'll be able to access things through the recordings. So for weekly homework, homework is not a required piece to this series. You can attend and not necessarily follow the homework. The homework, I think, if anything, will add to your learning and your retention as you go through. We need to make sure for those who do want to follow along with the homework and want to receive credit ultimately for the end of the series, please complete and submit all of the homework on the Microsoft form that was linked out in the emails that were sent out. And we asked the final due date for this is April 9th, which is 2 weeks after the final session. This will give you opportunities to sort of wrap things up, especially maybe you haven't had the opportunity to sort of follow along every single week. This gives folks the opportunity to sort of work at their own pace and still receive credit. We sort of have 2 tiers of credit. If you submit homework for 4 sessions or more, you'll receive a beginner ALCF AI for Science on Supercomputers digital badge. And this digital badge will have coded in sort of all of the information from this series. For those who complete work for all 8 sessions, you'll essentially receive the advanced badge for this. And for ALCF user accounts, for those of you who don't have access to the machines yet, we're still working on account requests, especially for those who may have submitted very recently. We're still processing them and trying to get everybody access. If you have any questions about accounts, you can direct them to the ALCF Help Desk Slack channel. I think that'll help as far as facilitating answers, and you'll get the quickest answers by going to this specific Slack channel instead of pinging people over email. And then people sort of can guide you from there based on what the needs are. So just a couple series guidelines to be mindful of. Something to know is we want everybody to be curious and ask questions, especially when we have opportunities to do hands-on exercises. Be respectful generally to all participants. And I think something that's maybe very important is that no one has monopoly on wisdom. I think there are probably a lot of you who have interesting backgrounds and understandings of AI, or more generally other things in computer science or computational science. So please share that if you want to, and also recognize that if somebody is oversharing, then we can sort of facilitate that. So be cognizant of sort of who's speaking. And also we're sort of here to learn from you as well. So the instructors here may know a lot of things, but they're not necessarily the knowers of all things in some way. So I think with that, I'll hand things off to Huihuo Zheng, who is a computer science here at the Argonne Leadership Computing Facility in the data science group. He's going to be talking today about just an intro to artificial intelligence on supercomputers generally. So with that, I'll stop my screen and hand things off over to Huihuo.
Okay, everyone, good afternoon. I'm Huihuo. Before I share the screen, I just want to briefly introduce myself. I'm a computer scientist at ALCF, Argonne Leadership Computing Facility. I had a physics background, so I got my PhD degree in physics from UFI. in 2016, and then joined Argonne as a postdoc, and then remained as a computer scientist. You know, I used to do a lot of physics research, but then the research I did was using supercomputer to calculate the material properties. And so then after joining ALCF, I do more and more supercomputer research, you know, and then AI. I started doing a lot of kind of AI since 2019. You know, right now I do a lot of work on how to scale the AI application on supercomputer, and then also how to manage like huge amount of data set to load efficiently for AI training. So, and I hope you know, this afternoon's session will be interesting and easy to understand. You know, I try to make everything as simple as possible. But then also, if you think deeply, you will find that also the concept is very profound. And so just give me feedback after you're hearing all the lecture, because I constantly, you know, even my son and my daughter ask me what I'm doing at Argonne. You know, I want to make sure that I have an easy way to explain things. So with that, I will start my sharing. And so for all this training series, we will be using this GitHub. And this is, I guess maybe someone can post this link to the Slack channel. And essentially it's located in the Argonne LCF. And it's an AI science training series. And you can see there are a lot of lectures. And other lectures is not updated. It's still last year's materials. And for me today, we will be talking about this, the first one, Intro to AI on Supercomputer. If you click that one, and essentially I will talk about like three things. The fourth one is just a very brief introduction about the following on lectures from other speakers. But the first three is the kind of my main contents. And the first one is the evolution of computing systems. You know, so I'm pretty interested in history. You know, I want to kind of understand where things come from and how things evolve. And so I will take you through this history of computing, starting from a very simple elementary level and all the way to supercomputer. And then I will talk about the concept called parallel computing. This essentially a technique how to run code efficiently in parallel on supercomputer. And then on you will see that supercomputer essentially a lot of CPU, GPU, or a lot of computer bind together and then into a big one. And so the parallel computing is a way to tell all the different pieces of the supercomputer how they can coordinate and work together and to solve the challenging problem. You know, so we will see a very simple example as you later on you'll see. And the third one, I feel that this is a kind of interesting one, is I want to explain AI and especially the large language models in a very simple way. You know, many of you probably use ChatGPT for a lot of purpose. You know, I personally use ChatGPT to correct my writings, you know, grammar mistakes. So we will see from the high level perspective how this large language model works, you know. And so, but let's go to the first one. For this first one, okay, this is the notebook I prepared. You see, there's a lot of figures here. So for now, you just focus on the photo, I mean figures. You don't need to focus on the text. The text with a detailed explanation, you can review it afterwards, you know. And I will explain everything verbally, the photo. And so when we consider the computing, you know, I always think about yes, I mentioned I have two children. My son is 6 years old. My daughter Phoebe is 4 years old, and I taught them how to count and also how to add like two numbers together, right? And I guess many of us still remember when we were young, we were told by our parents that the way to count, I mean, the way to do this addition or subtraction is that we have this 10 fingers, right? And so if you do like 3 plus 2, then you do 3 and then 2, and then you count 1, 2, 3, 4, 5. Then you got 5, right? So that's the kind of the most, the simplest way of computing, right? And that's probably why kind of naturally we follow the decimal kind of system, not the binary. Computer use 0 and 1, 0 and 1, but we use it from like 0 to 9 or 1 to 10, right? So that's probably because we have 10 fingers. So I taught my daughter Phoebe in that way, and she pretty much kind of pick up things. But I found like 2 challenging she has. The first one is that it is okay if she just do like 2 plus 1, 3. It's okay, right? But then if I ask her to do like a 4 plus 7 and beyond like 10 finger, she got confused. Like she put like 4 finger, and then her finger is not enough for another 7, right? So this is the first challenge that she faced. She got confused that she cannot do that the addition of the 2 number if the result is bigger than 10, right? Because she only have 10 finger. So that's one of the limitation. The other limitation is also she actually used one of her fingers to do counting. So like if I do like 2 and then plus 4, then this equal to 6. Then she has to use both 2 hands, and she kind of got confused when she need to use another finger to do counting, right? So that's also another kind of challenging. But then 2 weeks ago, my wife asked me to join the Parents' Day, and so she was taking school at DuPage Montessori School, and I found this a very good tool. I don't know how it's called. This kind of thing. Maybe I can call it counting beats, So it has like 1, 2, 3, 4, up to 9. And actually the photo I show here only have 1 set of this, right? And in the school, they have 2 sets. One is hanging on here, and then the other set is on the triangular place here. So then my daughter was given with a sheet, like with a lot of kind of number addition, like 3 plus 4, 6 plus 7. And now I see that my daughter, it was very good at counting. She just basically, if there's 7 plus 4, put 7 from here, and then 4 from here, and then she starts counting 1 until 11, right? And that's how she did the this calculation. And I found that she's pretty good, almost like she can finish 1 equation in about 3 to 5 seconds. So you can see that with tool that kind of help us a lot, right? And this tool kind of help us to save the number. We don't have to remember the number in our brain, that 4 plus 7, or if it is a bigger number, then we got, our brain can now kind of memorize number, right? So the tool help us to kind of store the numbers. And then, of course, in this case, you see that still we use our brain to do counting, right? But then later on, now we see that we have the computer, actually, the brain, it's also inside of the computer. It can do the counting, right? So this is the kind of, and I see like interesting. And so historically, people realize that this 10 finger is not enough. So in ancient China, this is like a 1600 before Christ and BC. So people use actually this called counting rod. And if you are Chinese, you know this character means counting rod. The first one is counting, and then the second one is rod. And actually this one can also mean chopsticks. So, and the top of this 2 character means bamboo. That means that actually in the early days, the bamboo was made the chopstick was made by bamboo, and then people used the bamboo, the chopstick to do this kind of calculation. And then different layout of this counting rod means different number, right? So you don't have, if you do like 100, you don't have to use like 100 chopsticks to represent the number 100. It's actually, there is a way, if you're interested, you can see here, there are different layout representing the different value of the numbers. So it's quite interesting. And then later on, people find a kind of better way, and this is called abacus. And there are different versions in the history for abacus. The version I shown here is from China. And essentially, you see there are different beads. The lower panel have 5 beads, upper panel have 2 beads. So each piece on the upper panel represent 5, and the lower panel, each bead represent 1. And for example, this column represent the number 8, right? And people can use this pretty kind of to do the calculation pretty fast. When I was young, our school, elementary school, still teach us how to use this abacus, you know, and then we have a lot of kind of sentence for us to memorize the rule to do this calculation. And this kind of can, on one hand, save the number and also provide a very good way to do the calculations. And later on, people invent other kind of things. And this one I find it pretty interesting is that it can do a very complicated calculation. It's called slide rule. It can do addition, subtraction, even exponents, you know, division, exponents, and square root. It can calculate like square root of 17, you know. If you are interested, there is a document, like you can go into detail how to see, and you can also search on slide rule on Wikipedia, Google, and find out the rules. And there's a kind of people, I was amazed how people come up with all these complicated rules to help the calculation. And so all of this tool invented before, it was kind of doing a manual way. We use our hand to do that, and still need our brain to some extent to help with the calculation, right? People start to think about, is it possible to just let the device or calculator or computer, whatever you call it, to help do the computation, and then to free the kind of calculation in our brain, right? And so this tool are the mechanical calculator. This is invented by 2 mathematicians. One is Pascal, the other Leibniz. And so the first one can do addition and subtraction. So you just put the first number and then add the second number, and automatically this machine will tell you the result of that addition. You don't have to use brain to count at all. All right. So so they have some kind of computing power in it. And this one is more advanced, not only addition and subtraction, but even multiplication and division. And so these are kind of mechanical thing. And then you probably know this the first computer, the real computer, you can say, is invented in 1945. And this is in the beginning was for the US Army usage and developed in University of Pennsylvania. And this computer, if I can call it, is really a super one, super in terms of size, not too much on the computing power. The size of the computer is very large. It's occupied more than like 1,500 square feet. And if I remember correctly, the weight of that is more than 40 pounds. And then it's made by electronic components, like specific is a vacuum tubes. This is a kind of very early version of these electronic components. Nowadays, the computer that we use transistors. But early times it was vacuum tubes. It's very big vacuum tube, so you cannot kind of put too many of them. And then also that's why the size of the computer is very large, right? And it's very complicated to use that to do programming. It can do programming, but it's very complicated. Every time you want to do programming, the person has to manually pull out the panel and then put it back, right? So you see a lot of people have to manually have to be there to operate the machine. And then you may be kind of interested in how fast this one can do, right? It can do like 5,000 operations per second, right? 5,000 operations per second. I was curious about how fast our brain can work. My son has a kind of addition books, like basically a lot of equation, and then it give you 1 minute, how many of them you can finish, right? And I think for me, I can do about like probably 100 per minute. So it's kind of maybe two equations, two operations per second for that particular case, right? And so this machine can do 5,000. So it's already a great improvement, like 5,000 operation. But still, compared to nowadays, the machine, the device that we have, like this form, it's very, very slow, right? And then in the similar time frame, we have the electronic calculator. Nowadays, we still use at school, but the version that we use right now probably much complicated than in the 1970s. But anyhow, this is a kind of smaller one, and we can do simple calculations and with this electronic calculator. And nowadays, so we have laptops and tablets, phones, and the power of this, it's as Paige already mentioned, it's in the teraflop range. So teraflop is 10 to the power of 12, right? This is 1 million, right? 1 million. So this is the kind of several order of magnitude faster than the supersized computer in 1946. Why we are able to make it faster and smaller, it is because the semiconductor technology. And you may know that the fundamental unit of all the CPU or GPU is the transistor. And this two plots show here, the left panel is how many transistors in a CPU or a GPU, right? So you can see in the beginning, in the 1970s, it's within 1,000. You just have 1,000 transistors. And because the size of that transistors is pretty big, this is the nanometer. This is the nanometer. So basically, this is in the millimeter range size in the early times. But nowadays, the size of the transistor is smaller and smaller, like in the nanometer range. And so eventually, this you are able to put more and more transistors, and that increases the power, computing power. But still, as you may know, that the transistor cannot just keep reducing the size. It will hit because if it is too small, it won't be stable. It will hit the effect called quantum mechanics effect. And that's why people think about the ways to go beyond this limit. This is called Moore's law limit. Moore's law will break, and when it is the size of the transistor, it keeps reducing, right? And so there are kind of quantum computers being invented, and nowadays, kind of these things become more and more promising. When I was in my PhD, I kind of didn't believe that the quantum computer would be realizing in my lifetime, but now so many years past, I see that this has become more and more promising. Maybe 10 years or 15, 20 years from now, you will be using the quantum computer more and more. Okay. Then at ALCF, because recently, probably after I graduated from my PhD 2016, the AI become more and more kind of popular, right? So it's compared in my PhD time or before my PhD, just traditional simulation, scientific simulation, is that we have an equation and then we do simulation and to learn the physics. But nowadays, AI becomes so popular. And we find that the traditional computer cannot really solve these AI trainings in a very good way. So there are many novel architecture being invented in the past few years. In ALCF, we have several of them. I list here. And then we will have a lecture next few weeks and to talk about the AI testbed. And you will have the opportunity to use this AI testbed as well. Okay, now the supercomputer, right? So all the things before I'm talking about like just one unit, one laptop or one computer or one AI accelerator. My supercomputer essentially is to, as I mentioned before, connecting like multiple of them. This multiple is in the order of thousands or millions of CPU or GPU together and into a big system. So you see a lot of cables here. And there are some kind of numbers to show that if you pull all the cables and then it can surround the Earth equator, but many times. I forgot the exact number, how many times you can surround. But anyway, this is a very, very long cable, sorry, and in order to kind of to connect all of them piece together. And so the key is that how to manage all the different components together. So they will be working together to solve a big, large-scale challenge problem, right? And there are need for solving this supercomputer. Here I show there's a solving large language model like GPT model, and you can focus the 3 column here. This means that those sizes are pretty big, the number of parameters in the model, and then there's the number of GPU like NVIDIA GPU that you use in order to solve this problem. The time scale you can see here is in the number of 100 days. Right, almost close to 1 year. So basically, if you want to train this model, you will use like hundreds of thousands of GPU, then you will need to train 1 year. So that means that if you use your laptop to train a big like ChatGPT model, it will take you maybe the entire lifetime to train. So that's why we need like large supercomputer in order to train this model efficiently, so that hopefully it can finish the training in weeks rather than years. And this is a brief history of the supercomputer. It's the power is increasing, and the earliest one is in the 1980s or 1990s. And as Paige mentioned, that actually the currently the phone that we have is very powerful. It can be like more powerful than the supercomputer in the 1990s. And this plot shows our ALF-CF system. Paige already showed that before. And this kind of the early times BGL system, it's not so kind of powerful compared to the current phone or laptop that you have, just a few times faster, right? But now what we have on the Aurora is probably this around like 100, close to 1. This is 10 to the power 18, and this is 10 to the power 12, right? So it's 1 million, almost 1 million faster. And then you also can see what are the science application that with this supercomputer can solve. Because of the time, I just leave you as the kind of exercise later on to check this website to see the scientific problem in physics, chemistry, biology, that what kind of challenge problem we can solve. And you will also hear more and more from the science speakers on that. So for this, let's go to the second one, parallel computing. So parallel computing essentially is to make sure that we can coordinate different pieces, like for example, different CPU, different GPU, to solve the problem together, right? And I will just show a very simple example, just calculating the pi here. And first, let's see how we can do if I just have one GPU, one CPU. The way we calculate the pi is that, okay, we can drop a lot of points in this square. And the square, the area of the square will be 4r squared, right? The width is 2r, and so the area of this, and then the area of the circle enclosed inside is pi r squared, right? So if you see, if I have a lot of points equally distributed in the square, then the number of points inside this circle divided by the number of points in total should be the same as the ratio between the area and the ratio of the area between this circle and the square, right? And essentially, the simple math you can calculate is the number inside divided by number total is pi over 4, right? And So you can, I have this simple example. This is not using the parallel computing yet. And so you can see, yeah, I guess I don't need to go into the too much detail of the code, but essentially just generate a lot of points that X, Y together is a random point, and then calculate if the point is inside the circle, the number in at 1, right? So then calculate the total number of points inside the circle, and then divided by the total points, and then times 4, it will be essentially the pi. So this is a thing, and actually you can run that. Let's see, we can go to the Google Colab to run that simple example. So the way to do that, I also provide this instruction. So you click this link, and then hopefully you sign in already. And then you can do, if you, maybe after you sign in, you will see this phase. And then you can open the notebook and choose the GitHub and provide the link. Yeah, then it will search the corresponding GitHub repo. I have a lot of them, and the one that we're going to use is the AI Science Training Series. And so it's the first one, MPI Pi example. Okay. Then, so this is the same notebook that I showed before. And this, the first one is the point. We can run this. Yeah, just run anyway. And then it will show, yeah, you can see it start to drop the points. Draw the point, and it will calculating. Here I show that the number inside, as the number of point increase, this the value calculated will be closer and closer to the overall, I mean to pi. And this is kind of on Google Colab is very slow. If you actually, another way of running this is on using Jupyter Notebook on Polaris. Later on, I think probably we'll have maybe after the lecture, you can follow the instruction to run this example on Polaris. And so, but here you can get an idea, yeah, and the way we calculate this pi. Now, I'll just stop here, stop the running, but it will just keep running, and then the value will be closer and closer to 3.14. This one is the, how, if I have multiple CPU, how do I calculate that, right? So essentially, because say that I want to draw this, for example, this is the 5 million points, 5 million points on the square, right? And then maybe I have 5 GPU or 5 CPU to do the work, right? So I can just the first CPU draw the first million point, second CPU drop the second million point, right? And then they all kind of gather together, like maybe from the first one get about 4 million, I mean 900,000, whatever, right? And then second one get how many points inside, and then eventually I add all of them together so that I know in total how many points was inside the circle, right? This is essentially what it does. So each CPU work independently. This command is basically what I say is that distribute this 5 million on different CPU, and so they work on different points, and then so they all drop the points on the square and eventually calculate the inside, how many points inside, right? So each CPU will have a value regarding how many points inside, right? And then I do this, this one is the total or reduce, if you know a little bit about the MPI, or reduce essentially adding up the value, this variable result. This is the number of points inside from all the CPU, right? And so CPU 1, CPU 2, and then we know in total, right? So then we eventually will calculate the pi, right? So you can see the way the improvement from this parallel version is that in the first version, if I do 5 million, then only one CPU doing that 5 million. So that one CPU has to drop 5 million times. But now, since I have 5 CPU, then I only need to drop like 1 million times, and all the 5 are working simultaneously, concurrently. So therefore, in principle, I should get speed up 5 times, right? So if that's how we do things faster, by coordinating these 5 together. And you also see there's some kind of communication. And in this particular case, the communication is very minimal. It's just kind of adding all the number of points inside together, right? And so you can also run on this Google Colab. Basically this one will kind of download this MLPerf example and then install the dependent software, and then later on, this installation will take a while. So I just skip this, but the result of that is that eventually you can do like one CPU is using MPI run. So you increase this value, you will see the result, the pi, and then eventually there's how much time it takes, right? So if you use only one CPU, then it will take 5 seconds, right? This two CPU, it's kind of 3 seconds. It's not like 2.5. There's some kind of overhead here. If you're interested, you can dig out, or you can ask me later on why it's not 2x improvement if I use a CPU, right? And then you can also do 4, right? So this is a kind of how you can get a sense about when you do the parallel computing, you can make things faster, right? You can also do things on Polarius by logging to Polarius through all these commands and check that Polarius will be faster than the Google Colab because of the hardware is much better, right? Okay, so this one is the on AI. So with the pi is very simple, right? So how about if we do AI? I just give a very brief high level since how we distribute the work to different CPU or GPU. Later on, we'll have another lecture dedicated to this, how do we parallel AI model. But essentially, AI is a neural network, right? So if you have multiple GPU, and then this neural network will process the data. So there are 2 ways of dividing the work. First is that we just divide the data set. So like GPU 1 work on part of the data set, GPU 2 on the second part of the data set, and then they work together, work concurrently. And so this way is kind of very simple way of dividing the work. So this will kind of more or less increase the time linearly with the overhead that they still need to communicate with each other each time during the training. And then the other way is that say that your model is very large, then you cannot fit the entire model in a GPU. Then you have to split the model to different parts. Like for example, here, the first layer on the GPU, first layer of neurons, you will not like little more and more, this point represent the neurons. And then in the neuron, there are values associated to the neurons. And so GPU 1 will work on everything related to the first layer. And then GPU 2, GPU 3 work on this part of the second layer and third layer, and then GPU 4 on the last layer, right? And this way kind of split the model. We call it model parallelization. And then, so the key is to make sure that all of them kind of work in a low balance way. And basically, I'm not like when you probably do a lot of project with a small group of people, and when you do a project, I always find that probably in the whole group, 1 or 2 person do the majority of the work, and the other people just sitting there idle, not doing too much work. And at the end, after the 2 people figure out all the answer, and then the rest of them just copy all the answer, right? So this is not a good kind of low balance way of distributing the work, right? So in the parallel computing, you will find that the most important thing is to make sure that all the workers, all the CPU or GPU have almost equal amount of work. And this is the guiding one principle. Guiding principle one. Guiding principle two is that they don't talk to each other. Especially they don't talk to each other unnecessary things. That will slow things down. Anytime they communicate with each other, that will take time, right? So if you can find a work that find a way of distributing the work that is not too much dependent on each other, then the communication among those different workers will be less, and then you will just improve the efficiency linearly, right? Okay, so this is the simple way, and then maybe later on you can learn that. And I guess because of the time, I go to directly another aspect, contents of this is the AI, and then kind of top level understanding of this. And we will also, you can also learn this. I'll show some simple example. Okay, so this notebook also you can run in two ways. First on the Polaris with Jupyter Hub. Second one is Google Colab. I will just again use the Google Colab version way of running this, and it's is this one. Okay, and we can skip. First, the contents of this one notebook, I want to show that on a high level, what is the AI training? And then how does the large language model work, right? And then show a very simple example. This is the linear regression. And actually the linear regression can be considered as the simplest AI model. And you all kind of, probably most of you know the linear regression. And so it's an easy way for us to understand. And so this is a kind of overall thing. And so then the first question is, what is the AI training, or how does AI learn things, right? And recently I start to kind of think about this, I want to kind of demonstrate this with the way I learn English compared with the way my daughter learned English. So I learned English starting from my high school, and I was told by the teacher give us a lot of rules. Like when you describe things in the past, you should use the past tense. When you describe things in the future, you should use the future tense, right? And I found that I always made mistake. Like I said, like I see a dog yesterday, right? I should have said that I saw, right? Even probably during this lecture, you already heard a lot of my grammar mistake when I present, right? It's because I learned this through rules, regulations, and it's hard for me as a second language, English as a second language, to kind of memorize all the rule and follow according to all the rule, right? And I found that my daughter learned things completely different. She was not taught by the rule, the grammars, but she just listened. She listened the English from TV, from her teacher, classmate, and from her older brother, Nehemiah, who kind of 2 years older than her and speak English better than her. So she just, through talking to her, and then she just automatically pick up things. And she was able to, to say things accurately. Like, I saw a dog yesterday. Well, many times I will say, I see a dog, but she doesn't have this kind of problem, right? So this is how the way she learned English is by having a lot of input of the sentences. Like, for example, I went to school yesterday. He played basketball last week, right? And then maybe some sentence like, I will go to UK to see my cousin tomorrow. And so this is a kind of future tense, but hearing a lot of things, and then the brain just have certain way to kind of figure out the patterns behind all the data, right? So I found that this way of learning, or this way of things, nowadays people call data-driven, is very, very powerful, right? So now I kind of realize that many times I try to use rule or regulation to tell, like, Nehemiah, don't do this, or Nehemiah, don't fight with your sister. He always rebel and fight with her sister, right? So human nature always kind of rebel against the rule. But if we show a lot of pattern, like we ourselves as parents present good pattern, and then we find that, wow, the children just automatically pick up all the pattern, right? So the way of having a lot of positive input and then to allow the children get this positive input and automatically learn, I found is very, very powerful. Yeah, this is the kind of my way of kind of seeing how this AI model works, is that nowadays we have a lot of data, and then we design a neural net model, kind of artificial brain, to be able to learn from the data, right? And give you another example of this is, I guess, if you use the ChatGPT, then you kind of know. And so say that I have a sentence, I got an A+, and I am very, and I put this, ask you to fill the word here, I am very. Probably most of us know that I will feel like happy, right? Very happy, or very proud, etc., right? Many, many words. And you probably wouldn't feel, I am very sad, right? And that's because we know that if I got an A+, it's a good thing, so that I will feel happy, right? This is the kind of the reason behind our brain. But how the AI model works, or large language model works, is that the model see a lot of example sentences on the website, on papers, on a lot of resource that whatever the model is trained, and you see a lot of sentences like, I got a big present, I'm very happy. I will go to UK this weekend, I'm very excited. My mom brought me new shoes, I'm very happy, right? I got a new car, I'm very happy. And sometimes negative emotion, like I feel my calculus class, it makes me very sad, right? So it kind of statistically know that if good things, then I will be happy. Bad things, it will be kind of like sad, right? And so you probably wouldn't feel this, I got an A+, I am very surprised, right? Because it, wouldn't surprise unless you have a sentence before that, it says that I didn't study well, but I still got an A+, then I feel surprised, right? So this kind of how the AI model learn all of this is through this statistical kind of way, because we have a lot of data available on the website. It can kind of learn automatically from the data in a statistical way. Okay. And then I put two kind of example. It can do very complicated things like ChatGPT, write a point about Albert Einstein. This is a scientist, right? And then this is a kind of a religious people, Martin Luther. You can also, and you can find that you can follow the structure of a point and then also describe the contents. It's very powerful, right? Yeah, you can play it on your own. So this is a kind of, hopefully through this example, you can get a sense about how this AI model works, how the large language model works. Now, I will just quickly go through this example of this linear regression. So you're probably kind of pretty familiar with this Excel sheet where you have a kind of many points, and then you are asked to draw a line so that follow this trend of this point. This is called linear regression, right? Say that the example shown here is the tuition from different years, and say that we already know that so many years before. Now we want to predict the years. For example, this is a 2007. Then once we figure out the line, we can do the prediction, right? So figuring out the line is to learn the pattern from all the data points that we already know, right? And once we figure out the pattern, we get this model. In this case, the model is a line, right? The line, and then we are able to make prediction. So this is the simplest way of this AI model. And so just you don't have to see how all the codes, like you don't know what is Panda, NumPy. All of this are essentially some software tool for us to kind of do this problem. And so for now, you can just get an overall sense about how these things work, right? So this is a kind of dependency library in order to do this exercise. And this is the data. So the data here that we want to do the linear regression is the housing price data. Basically, we have the area of the square foot area of the house and versus the price, right? The larger the house is, the larger the price is. So that should be kind of a pretty reasonable thing. And so we get the data, and then we use the package to plot. This is to print the data, and this one is to plot all the data that we have. And so you can see it's kind of scattered around, right? But we have kind of correlation between this size of the area and the price. And so larger the area is, the more expensive, right? But we kind of want to figure out a line that is can capture this. And for this linear regression example, we kind of, because it's very simple, this line usually described by the slope and intercept. This how to get the slope and intercept is already, you can figure that out based on all the data point. And so this mathematical theory is very simple. So you can find here. I give the link, right? But the purpose of this notebook is I want to use the AI training way of getting that. I don't want to just use this formula to calculate slope and intercept. But this provides a way for me to check whether the answer I get from the AI training is the same as the exact true result, right? So we will just compare that, and then this is the finding how many data points that we have. So I will just print it out. So in total, we have about 500 data points here. And then these are the X and Y. X is the square footage, Y is the price. And you can also print out them. X, this is square footage, is a one-dimensional array, contains all the numbers of the area of the houses. And so according to this formula, whatever we are doing for now is just calculate the exact M and exact B that we should have. And so these are just formula. I just quickly go through. And so we just run all this step by step, and eventually we can figure out M and B, right? So M and B, and then the line is this. Is 87 point something times the square footage plus the intercept, then you'll get the price. And we can plot together with the original data. These are just the function, how to plot the data point and the line get together, right? So this is the regression, linear regression, the result of the linear regression, right? So basically this is based upon the theory, the equation that we have. So now, how do we use the kind of AI way or training way to get the same kind of answer, right? So essentially, this is the first, I know that this is the model that I want to describe is a line, right? So, but I just put a M and B in the initial guess, and then I just adjust M and B so that all the point that this white hat will be close enough to the real data point, right? And how do I quantify the close enough? That is a term that is in the machine learning called loss function, right? So and the method that we're going to use called stochastic gradient descent. We will have more kind of information maybe in the next lecture. But for now, it's just essentially we adjust this M and B so that overall the line, the predicted value will be close to the real value, right? And the function to capture, to categorize how close these predicted ones with the real one is the loss function, right? And basically here the x-axis is the M. I'm adjusting M or B so that this loss function will have different value. And the lower, the better, right? The lower means that the distance is small. The discrepancy is small. So eventually, I may have start with a point, like for example, I start from a point here, and then I just adjust M. And then eventually I want to, eventually I want to go to the bottom, which is the lowest point, right? And so the way to do that is like I calculate the slope of this loss function. This is the kind of you're walking from the mountain and you want to find the valley, the lower point, right? You want to go downward, and so the way you just stand there and then figure out where is the direction to go downward. And once we figure out the direction to go downward, we just step by step walk downward, right? This is essentially the logic here. So this the differential here is the slope. And once we figure out the slope, we just go one step. And this step, how large is the step, is called learning rate. It is again another terminology. So we have the loss function categorize the distance between the predict value with the ground truth, the truth, right? And then we have the learning rate. And this slope is a gradient, basically tell us where is the downward direction. And once we figure that out, we just go one step. And then size of the step is the learning rate, right? And then we just go step by step. In this case, so this step value is what we choose. And it may be if we choose the step too large, it will jump from here to here. And then it just keep jumping around, right? So sometimes we want to choose a smaller step size and then you just keep going to the bottom, right? And of course, this loss function is very simple, but in reality, it maybe have a very kind of complicated shape and have some kind of local minimum, and this is the kind of global minimum. We want to find the best one, which is the global minimum, right? But if the step is too small, it maybe get trapped to this local minimum and could not find the global minimum. So the general practice is that maybe we use a bigger one in the beginning so it can explore all the different places. And then eventually, when we find a better one, we kind of reduce the step size to a minimum, right? This is how the way it works. But today, we just set the step size to a small number because this example is very small. So we don't do this bigger one and reduce it to a small one, right? So the way we do it is that first we tell the computer how to update this M and B. And these are the function, basically what I said, that figure out the slope, the downward direction, and then jump a little bit by providing the step size. Then eventually, this is a loss function we define, and we can go directly to here. Maybe I jump to the final code, and essentially, so we have the initial guess, the slope, and the intercept. This is the learning rate, how to change the slope and how to change the intercept, right? And then we do iteration. We just keep adjusting, right? In this case, I adjust for 30 times, right? So I get the initial B and M, and then I update according to the rule I defined, right? And then calculate the loss. And then based upon the loss, I calculate the downward slope, and then keep updating until a point that hopefully with this iteration, it eventually will become reduce the value. And if you run this cell, you will find that it will keep adjusting. So this is kind of the animation as every step. This is the third iteration, the loss is decreasing. And then you see the line, the red line is closer and closer to the blue line. Blue line is the one that we use the math way of doing things, right? So you see, yeah, eventually, finally, we will get this result, the same result as before, right? So kind of recap everything. Here is we kind of have a guess, and then we calculate how good the guess result is, right? And then we kind of adjust the model. In this case, it's the slope and the intercept, and then keep adjusting that, and until the loss is become the smallest, then that model is the best, right? So this is the essential kind of component in the AI training, that we have a model, and inside of the model have many parameters, and we just adjusting the parameter So at the end, the loss will become the minimum. Okay. And then we have a homework. So you can just run through all the cell on your own later on. And then this homework is that we call mini batch training. So in this case, I put the entire data set, like calculate loss. In the machine learning training, we might not use the entire data set all at once. Each time I adjust the slope and then the intercept, I'm using like just a subset of the data set, and then keep running over. Like next time I use another subset of data set, this is called mini batch training. And I describe how to do that, the essential components. So the homework will be that adjust this code so that it will do this training batch by batch rather than put the entire data set all at once at each iteration. And then there's also a bonus question if you have time to do that. And eventually this is a provided way how you can submit the homework. And the link here provide like how to do all these steps. Okay, so that's all I have. Hopefully through this lecture, you get a sense about what is supercomputer, right? Also the history of computing, and eventually also like you get a little bit sense about what is AI training large language model, right? And through this linear regression example, you also get a sense about the kind of training process, what it looks like. Okay, thank you.
Thank you so much, Huihuo. For those of you who might have other questions specific to what Huihuo went over today, please go and look at the Slack. That's going to be the best resource as people work through homeworks and also work through any of the materials each session. So now we're going to transition over to our science talk. So like I mentioned at the beginning of today, we will have a science talk every single session of this series, sort of spanning the entirety of all science domains. Today, the science domain specifically that we'll be hearing about is computational biology. I'd like to introduce Arvind Ramanathan. Arvind is a computational science lead at Argonne National Labs. He's a computational biologist and also at Argonne, and also a senior scientist at the University of Chicago as part of the Consortium for Advanced Science and Engineering, or CASE. His research interests focus at the intersection of data science, high-performance computing, and biological and biomedical sciences. So I'd like to hand things off over to Arvind and let him sort of give an overview of what he researches and what he focuses on.
Cool. Thank you so much. I'm hoping to share my screen and see things go smoothly. All right. So I think you've been seeing a lot of things that talk about AI and what can be done in the context of learning simple functions or simple ideas from what Huihuo was already describing. The context for why we are doing what we are doing in the lab, let me give you a little bit of history. So what I'm going to focus on is, say, how do we design new organisms or design life from scratch? And in that context, we are mostly interested in trying to see how we can design new proteins or new enzymes and new things that we can actually like bring to life in the context of biological systems. So mostly this is focused on this idea that we can bring together aspects of robotics, aspects of AI, and biology together to solve some interesting problems, from biomedical discoveries to like trying to understand, for example, how SARS-CoV-2 evolves. So one of the first applications that we actually did was that we built what are called as foundation models for genomic data. And these models are essentially like ChatGPT, very large models trained on huge amounts of genome scale data sets. And they were fine-tuned on SARS-CoV-2 genomes that are available, nearly about 1.5 million sequences from the first year alone. And then we decided that we should test the model in terms of like looking at the next few years worth of SARS-CoV-2 data and see if we can predict all the emerging variants. So for example, Delta, Omicron, Iota, Eta, Gamma, all these different things, just by looking at Alpha and Beta as these two main strains of data that were provided as training data. And in fact, one of the things that happened as a consequence of doing this, which basically took a lot of compute time on our systems, was that we actually got awarded what is called as the Gordon Bell Prize for high performance computing applications in COVID-19 research. And the ability to basically build these pre-trained transformer architectures for nucleotide data was actually kind of a big deal, because at the scale at which we are actually training, it would take at least a couple of weeks to train these models on the entire supercomputer. And we basically also showed that it is possible for us to observe nearly linear speeding on these models in order to make them converge in less than half a day, right? So if you were to take 2 weeks to train and converge these models on a supercomputer like Polaris, which has 2048 GPUs, it only took about 0.5 days to train it on the Cerebrus architecture. And by generally doing this, we were able to say we can predict these new variants that are out there. For example, even the BQ1 variant, which means that this model is actually able to like tackle real world cases. For example, if you want to predict new emergent cases of like SARS-CoV-2 or other viruses in the wild, for example, influenza variants, or you might be interested in doing, Zika virus or other sorts of variants that are important to kind of see. Now, how can I use this ChatGPT sort of idea? One thing that we do in the lab is to actually build experiments that allow us to, design new enzymes or new synthetic genes that we might be interested in doing. So this is actually an example where we can take these pre-trained large language models, use these models as sort of a reward function that can be rewarded through experimental data. So for example, I can say this protein expresses well in the lab, and therefore I'm going to assign it a bigger score. Or I can use some structural metrics from a prediction like AlphaFold. AlphaFold, if you have not heard, is this protein structure prediction algorithm that was built by Google DeepMind. And they were able to show that they're able to outperform any other structure prediction code out there, which is kind of cool that they're able to do this. But one of the things that we wanted to do was how do we take this to the next level of integrating these reward models and then generating new examples that kind of align with this idea that these are really new synthetic genes that have not been seen in the nature. So what you see on the right-hand side is this generated sequences that are shown in the colored dots here. And this is from the natural sequences that are shown in the grayscale. But what I want you to observe is this little corner on the top, because we were kind of like steering the model towards it. The model was steered in a way that could actually like generate new sequences that are not seen in any of these gray plots. And you can hone in on some of these plots and say, okay, can I select a few sequences and put them through this experimental data for predicting what the catalytic rate of that enzyme might look like in the wild. So when we did that, we can actually simulate that entire process. And one of the things that was really cool was the fact that when compared to the wild type, which is shown as the purple line here, which is called 5-MDH, it is from the bacteria called E. coli, which I'm sure you would have heard of. What you can see is many of the designs that we had are quite productive. They actually have lower energy of activation, which is kind of very cool because we never told this about the fitness function or something for the model to learn, but somehow it has actually captured some evolutionary details that tell it that this is the direction you want to go if you want to have better catalytic rate and so on. So one of the other things that also came out, which was a very cool observation, is the fact that from the experimental assays, just one round of it, we could demonstrate that we could get better at expressing enzymes. So out of the 96 designs that we tried, 89 of them expressed, and 48 of them actually have this malate dehydrogenase activity, which is like really high level of expressibility and also high level of like yield that you get per experiment. Now, what we are trying to do with this is to close the loop with respect to taking this experimental data that we got and feed it back to our generative model so that we can actually like generate new enzymes that have far more activity than what is found in the wild type. Now, you can ask why this is important. This is sort of important in many synthetic biology applications. For example, let's say you want to produce a medicine in the lab, or you want to say you want to produce some sort of a protein that is involved in like beer making. And again, beer making, textile making, all these actually use enzymes at very large scales, but they are usually restricted by the amount of production that they can get in the natural world. So a slowing step is essentially to design highly functioning enzymes that can still work, but not overtake the sort of population that they might have inside the bioreactors. So we are really pushing hard in terms of like saying, can we generate these new enzymes or generate designs of these new enzymes that we can rapidly evaluate in the lab and go forward? So this is one example where we can do this. Further addition to this is the fact that now I had this model suggest this experiment. I had this model suggest, how I should do this in terms of like running some, experiments as such. But we could basically ask the AI itself to do the experiment, right? So this is an example where the vision is essentially to start out with this very high level goal of saying, I want to design a protein that has this function. So for example, let's say I want to design a protein that can basically break carbon silicon bonds. Now you can ask why this is important. The carbon silicon bonds are something that is found in almost all electronics. So you want to basically get rid of them if you want to do like processing and recycling so that you can actually get more silicon on one side and carbon on the other side. This is not a bad idea, especially if you want to like do separation of these elements for like battery design and things like that, which can be used in a different line. But if I were to give this as my view, saying that I want to give the robot a high-level description of this hypothesis, and it basically enables you to continually work out what those experimental hypotheses should look like and either confirm or reject that hypothesis on the basis of what is given. So we basically are using AI and robotics and simulations to close the loop by planning, executing, and analyzing these experiments on the fly. So in fact, here is this virtual world that you see on the left-hand side. And the right-hand side, what you see is the actual implementation of it. Basically, this is a self-driving lab that does this experiment called as polymerase chain reaction. So this is a very baby step in terms of asking the robot to essentially learn how to do this protocol in the first place. And then I'm going to show you how the code was even generated by the AI to do this. But this basically builds on a lot of approaches towards planning, machine learning, and simulation to kind of design these experimental properties and outcomes that we care of, and automation of these experimental protocols at scale so that you can sort of do any design experiments in the lab without having to have human intervention. So there are like labs out there which talk about cloud labs where you have automation at much larger scales and so on. But what you might quickly realize is that the automation is actually enabled by humans, which is that the humans are always loading the samples. Humans are always bringing the instruments together to kind of achieve the experiments that you want to do. In this case, basically what you see here is that the experiment itself is kind of learned by the robot and then optimized for the set of equipment that we have in the lab. So this is a sort of application where you can have AI completely run end-to-end campaigns on the experimental side. And this is sort of linking a lot of the facilities that we have inside the lab. So for example, we are interested in designing new antimicrobial peptides. And in this case, we might have an antimicrobial that has to act on a new strain of bacteria that we might not even know what it is in the first place. So what you can do is I can go and say, I have all these peptide libraries that I have built up. I can query and understand what that peptide is actually like capable of. This is where one of the agents, as we call them, this is a large language model based agent that can actually kind of synthesize new knowledge for you from ChatGPT and other sort of software to kind of get ideas on what these peptides might end up doing. You can then sort of identify what targets that those peptides might act on within the context of bacterial proteins. So you actually align the proteins, predict the structures, and you can sort of rank the structures on the basis of the results that you get, which tells us a lot about the function of these peptides and whether they might have action on these bacterial strains that we are interested in. And then once you do that, you can actually ask the BVBRC agent, which kind of tells you how to filter the results. Because if there is previous knowledge about the fact that this peptide acts very well, you can actually have that run on the same bacterial strain of interest and say, okay, I can get an answer for you very quickly. And so the first step is all driven by the AI in terms of formulating what that hypothesis might look like. The second set is basically agents that are built in order to run these HPC and AI resources, where I showed you an example of this ChatGPT-like app, which could go and design new enzymes. And then you generate these candidates for experimental evaluations, where the self-driving lab performs these experiments and sends this back as part of the continuous feedback that we need for these programs to sort of evaluate. So from the point of view of having these as embodied agents, what do we mean by that? Is basically that these are, large language models that are trained for a specific task, which are fine-tuned on the data that they have to see. So in this case, you have an agent that sort of has an idea what these tasks might look like, and then it breaks them down into these different hierarchies of subtasks that it needs to achieve. And then what it does is basically generate a code. So you have a task prompt that says, I want to do this PCR mixing of liquids that I have. And that basically generates a set of code and actions that are now executed on the robot or simulated on executing the robot. And then if it finds an error, it basically says, I'm going to go back and correct myself. And that correction is basically defined by the code itself. So the code itself learns how to self-correct its action. And then it can refine and add these new skills once it succeeds. And then it can retrieve and kind of like work through the whole code generation process itself. So this is like the scheme for like playing an entire game that is just looking at new pieces of code and saying, how can I assimilate new skills as I continue to learn on this data set, on the code data set itself? Now, you can ask if this actually works. This is an example where we used ChatGPT, for example, to come up with a simulation for a smart science factory. And in this case, the smart science factory is doing nothing but building sandwiches. And you can see how that actually works out.
In previous versions, I demonstrated that GPT-4 could be directed to design parallelizable experiments, which would run on virtual robots. And I introduced a system that allows clients to request robots via a template and an engine that can match these templates with available resources on the fly. For the new version 3, I have improved several aspects of the simulation environment. First, I built a live updating dashboard with which you can view the overall state of the engine, the states of each executing job, and the resources currently controlled by the engine. Next, I support controlling a new variety of robots, which can inform the engine of their properties and relationships to the rest of their environment. And again, these properties ensure that experiments are not limited to specific instances of robots. The simulation that we are watching here was designed to show that the engine can support these experiments that request robot properties rather than the robots themselves. And this implies that these robots can be selected from arbitrary locations in the lab while ensuring that they can coordinate with the other robots that are needed for their experiment. So if we submit the same job over and over, different areas of the laboratory turn blue as the engine dynamically distributes work to available hardware.
So what you're really learning is the fact that we can actually build out entire simulation factories of, what these facilities might look like in the future, specifically in the context of scientific experiments. And in that context, what I would also like to say is that we do have a training program for most people that are interested in doing this. We have the rapid prototyping lab that we built in order to like preview. So I gave you an overview of what these genome scale models can do. They can actually be used to predict new variants. That can be used to design new enzymes. It can be used to design cellular pathways and things like that. We have models that actually like convert protocols, like high-level description of experimental protocols into Python code, and then eventually be able to like do entire experiments at the lab. So with that, I'd like to take, thank you all for your time and attention. This is all supported by a lot of people in the lab. a lot of computing time that was allocated on Argonne's Leadership Computing Facility, access to a lot of the data, code, and models across the entire ecosystem that we have, and then funding, of course, by a lot of different agencies as well as other colleagues. So if you have any questions, I'm happy to answer them. And thank you so much for your attention.
Thank you so much.
I have a question.
Arvind. Oh, yep, go ahead.
Thank you. So have you actually synthesized an improved protein and then encoded it in DNA and stuck it in an organism?
That's exactly what we are doing. Yeah, we have.
Okay, so I mean, can you translate that into a specific example? You talked about beer. Maybe that's an example.
Yeah, that's an example. So what we have been doing in the lab is basically trying to improve the design of malate dehydrogenase, which is an enzyme that's involved in the Krebs cycle, if you know about it. That particular design has actually improved the enzyme activity by about 2.5 orders of magnitude is what we are seeing in the E. coli system that we are currently working with. There's more work that is being done to kind of organize it in a way that we can, adapt it for different organisms as well. So for example, one of the things that we have as an advantage is because we work with genome data, which is the nucleotide-based language models. These models are very good at learning GC content, or basically adaptation to specific environments. And so we can actually take the constructs that we get in one condition and just translate it to another condition based on these models. And those predictions are also being tested right now. So there's a whole variety of things that we are standing up on these models in terms of their ability to predict new things and predict and understand how we can use it for synthetic biology applications.
Cool. Have you run into any unintended biochemical consequences in your organisms? I mean, these are systems, obviously not single steps in processes, right?
So that's a great question. So far we have been trying out very simple things. I've not gone to the extent of manipulating entire pathways and trying to say what pressure it might do. We have done one experiment where we have looked at threonine production, where we have seen there are untoward consequences because it actually imposes a lot more on the organism to survive. So they don't survive really very well beyond a certain point. But we don't know what the consequences might be at the end of the day when it comes to having new, completely new sets of bacteria with completely different phenotypes and so on. So that's a really open question. I don't have a good answer for it.
Okay, thank you.
An excellent question. Thank you, Richard. So looking at the time, I think we will wrap up for today. So thank you so much for coming and speaking, Arvind. There's been a lot of thanks and fascination in the chat, so thank you for that. And so for next week, we'll have session 2. If there are any questions in the meantime, please turn to Slack. That's going to be your best resource moving forward. And as far as resources, all of the recording, slides, and all the materials will be posted online as we move forward. So thank you all so much. Have a good week, and we will see you next Tuesday.